Today I'm going to talk about mass assembly of galaxies and recent results in simulations. And I know for some of you it was a struggle to wake up early this morning, so I'm going to try to help you through it by suggesting tweets as we go through. So here we've got one. I'll be scripting my own tweets. Feel free to just repeat these on Twitter. I may or may not bet about how many tweets we can get during this talk, so don't be shy. Join on in. Twitter feed's welcome too. So here's the basic premise for this talk, right? There's two general ways to think about mass assembly of galaxies, right? And this, at some level, is the divide between what we do observationally and what we do theoretically. So on one hand, we have observational statistics. So we can look at things like the galaxy-stellar mass function. We can look at the mass-relative relation. We've heard not so much about the mass function. We'll hear about it a bit in the talk after this, but certainly about the mass-relative relation and the mass-size relation. On the other hand, we have physical evolution of galaxies, right? And so this is now looking at, for example, how we actually regulate or how we build up galaxies with time, how important things like feedback are, star formation efficiency, inflows versus outflows. And we want to understand what the meaningful link is here between these two, right? So we want to understand how we actually piece together a model that includes the physics of galaxy formation to reproduce some of the statistics that we see. The problem is that our models sometimes can be, to say the least, incomplete, right? And so we want to be able to do as much as we can with the observational data alone. And so this talks about trying to put together this meaningful link, how we can actually understand how galaxies are evolving just based off of the population statistics. So this is a compilation of mass functions. This one's taken from Peruzzi. And you're going to hear more about the mass function in the next talk with Kevin. The point is that from this you can already get a sense of how galaxies are building up their mass with time. Not in an individual sense, but going from redshift 8 down to redshift 0, you see this mass function building up, and it's slowly changing its shape. And people have been doing great work on this recently. This is going to continue to improve in the years to come. The question is, how do we now take this and learn something about what's actually forcing these galaxies to evolve in this way? And more importantly, if you identify galaxies at some high redshift epoch, what do they evolve into? Right? That's an important question to try to understand. Okay, so one way to deal with this is to use something that's known as constant co-moving number density analysis, right? So this is one method for forging progenitor-descendant links. So I take my mass function. This is a plot from Van Doken. I flipped it on its side so it sort of looks like other plots I'll show during this talk. But this is just a mass function. So I've got number density on the y-axis and then mass on the x-axis. And I've got a series of mass functions here. And what I do is I basically say, okay, the most massive galaxies at redshift 2 are going to evolve into the most massive galaxies at redshift 0. Same thing for the least massive. And so therefore the onsets that we can put forward is that if you think of this in a co-moving volume, in fact, galaxies preserve their distribution in co-moving number density space, right? This is a reasonable first order approximation. So you can draw this horizontal line at a constant co-moving number density, and you simply link galaxies together in that way. Okay, when you do that, you can now derive something like the mass evolution for galaxies. And this is from the same paper here. They're now showing how you end up building some massive galaxies directly from this data set. Moreover, now that I have the mass evolution of these galaxies, or I forge these progenitor-descendant links, I can now look at something like the size evolution of the galaxies, or for that matter, the Sirsk index, the morphology evolution of these galaxies. So observationally, this is how we actually infer some information about the mass buildup of galaxies. Right? The problem is that you can assume that this is not necessarily going to work. In fact, this is a zeroth order approximation, but we want to know how well does it actually do, and can we do better using simulations to inform how we actually draw those links. Right? So that's what the content of this talk is. This is now showing a series of redshift 0 ellipticals, and what we're going to do is we're going to be able to trace these galaxies directly back in time. Right? We can use the merger tree to trace these galaxies directly back in time. And then we can look at how they built up their mass. We can look at what processes were important to them. So for example, here we have these series of galaxies. If you look at them at redshift 2, they have similarities, but they're ranging over at least an order of magnitude mass at this time. Many of them go through merger events. Sometimes that changes their morphology, right? And this is going to be important to understanding how you actually build up this relatively homogeneous population at low redshift. Okay. To make this a bit more quantitative, this is now showing a series of Milky Way-like galaxies. So I'm showing the same thing as the previous plot. We've got a series of Milky Way-like galaxies. They're being traced out to redshift 3. Okay. Down here in the bottom plot, I'm showing the mass evolution of these galaxies with redshift. And then I'm showing the equivalent number density evolution of these galaxies with redshift. Right? So this is how they evolve in number density space. The colors that you see up here correspond to the colors of lines. And here's the point to take away from this. These top three panels, okay, these three show galaxies which don't go through any really significant merger events from roughly redshift 3. And you can look at them down here. The thing is that even though they don't go through any really significant merger events, they still have an order of magnitude mass difference by the time they get out to redshift 3. Huge discrepancy in their mass evolution. And that's driven strictly by the fact that they're sampling different parts of the star formation main sequence. Or really, they live in slightly different environments. These two guys down here, they go through mergers, and so you can see these discrete events where they actually jump in mass pretty rapidly. And in fact, when you have something like this system here, you can end up with a mass which is consistent, with a Milky Way type mass of redshift 0, but start from something much, much smaller at a redshift 3. And so this is the sort of problem that we face. Now, if you look at the evolution of these galaxies in density space, you should basically draw a couple of conclusions. First is that the constant number density evolution is sort of not what you should expect, and in fact, it's a little bit rare. Scattered growth rates are ubiquitous, and there's a contribution to the number density evolution that's driven by both the scattering and star formation main sequence, as well as the merger history of galaxies. So, looking towards the simulations, this is now showing a mass function that we drew from the lustrous. So we're now looking at the mass function out to redshift 6. What I can do is I can draw this band here. Okay, this band here shows a selection of galaxies that roughly correspond to Milky Way mass galaxies. Okay? I then find out where that intersects with my redshift 0 mass function, and I can form the exact analysis that would be done observationally. Right? I can then infer what the mass evolution of the Milky Way galaxies in the simulations is. And this is the result that I get. This is showing mass evolution as a function of time. The red band here shows what I get by simply looking at where this gray band, the constant co-moving number density, intersects those mass functions. The green line shows a observational result from Van Dalcombe looking at the mass evolution of Milky Way using, again, observed mass functions. And they agree pretty well. At least out to redshift 2 or so, they agree pretty well. Redshift 3, there's a bit of difference. That reflects the fact that we have stellar mass functions that don't exactly agree with what's observed. But now I can take these same population of galaxies and actually trace them back in time, use the information in the simulation to look at how they're evolving with time. Right? And that's the result that you get. So it's very different. Right? First, there's one or two orders of magnitude of scatter, right, that's associated with the evolution of these galaxies. It's really quite large. And second, there's a systematic offset between the median growth rate of the tracked galaxy population versus what you infer from the constant co-moving number density analysis. Right? To phrase that same conclusion in a different way, this is looking at the evolution of these galaxies in number density space. This red band shows the assumption of a constant co-moving number density evolution. What we find is that you have something that evolves a bit more steeply. Now, the positive conclusion you can draw from this is that this is something we can then parameterize and fit to, okay? And I don't expect you to be jotting these down. If you do, that's great. You can take some notes and go back to your computer and fill this right away. What you get from this is an evolution track for the number density evolution of these galaxies. So you can now say, if I start at a fixed number density, what will the median number density of that galaxy population be at some later time? Okay, so effectively I'm just tracking out this non-constant co-moving number density evolution, right? And we've got scripts that allow you to evaluate this. Again, it's a messy fit, but it can be done just as easily as constant co-moving number density analysis. Okay. If you do that, you can then invert the mass function, and that will then give you a mass evolution of galaxies, and you can see this now allows you to match much more clearly the seen mass evolution within the merger trees. Okay. The fits that we apply over a wide range of number densities. And an important point from this is that if you look at something like the Peruzzi models, which are abundance matching, totally different models, right? They're using dark matter only simulations and they're using abundance matching techniques. You can look at how their points correspond to ours in terms of the number density evolution of galaxies. What we find is they agree very, very well. Okay? The reason for that is that the scattered growth rates are ultimately driven by the stochastic growth of the underlying dark matter halos. And so for that reason, if you go to a lambda CDM cosmological simulation, you should find number density evolution that roughly agrees with what we're quoting here. The other important point is that if we performed this fitting, everything I've done so far has talked about stellar masses, and you could easily ask the question and in fact argue that the simulations I've used include prescriptions for feedback that are uncertain, as Brad was just talking about. But the number density evolution that we're quoting actually can be pinned down by the dark matter halos alone. And so for that reason, this is a more robust conclusion that we draw from our simulations. So I suggest these tweets here. Okay. Torrey shows powerful derived non-constant number density evolution trends. Amazing. Torrey shows galaxies evolve along non-constant number density evolution tracks. So, just to bring that point home, we get these tracks here, which you can now look at. This is a paper from really just a couple of weeks ago, looking at the mass evolution of the Milky Way. And really, this is not using the SAM, totally different model, right? Totally different physics put into it. And both the median evolution and the scatter that's found in the model really agrees quite well with what we're finding. So this is a robust result. That's one thing I want you to leave with here. When we quote this isn't directly tied to the physics in our simulations. Now let's take on a case study here for the scattered growth rates of compact massive galaxies. So in Redshift 2, if we select a population of compact massive galaxies, we can ask what's their fate going to be in the low redshift universe. This is a hot topic people have been debating for a while. So here we have our selection of galaxies. It's in a specific mass range below this sort of compact selection line. If we track those galaxies forward in time, this is what we end up with. All right? There is not some single distribution of galaxies of low redshift. In fact, these things are spread over an order of magnitude in mass. And we can pry into this in the simulations and look at what's actually driving this. This is work that's been done by Sarah Wellens. We're now going to take these galaxies here, which are color-coded, right? So we've got these blue galaxies, these orange, green, and red. And the color is going to match what you see over here. We've got 4 different tracks that these galaxies can follow. The first is that it's possible for these galaxies to be consumed by something yet larger. And so as you look at this plot down here, the color is showing where the original stars live from the galaxy that we selected at Redshift 2. So blue represents the original stars, red represents stars from something else. And here you see this thing moves into a larger potential, and by the time you get to low redshift, you cannot find this galaxy anymore, it has been consumed. There's also the case where you get this galaxy evolving into the core of a low redshift elliptical. Okay, so here this thing survives, it does accrete some low mass galaxies, it's sort of puffing up its halo. But by the time you get to low redshift, it now lives as the core of a low redshift massive elliptical. We've got the mixed situation where you have a major merger. And so then you still kind of have this galaxy at the core of a low redshift system, but it's now been thoroughly mixed with another compact guy. Those are pretty rare. And then we've got this situation where these things live and remain relatively unperturbed. And those are the systems that don't grow too much within this space. So to summarize that, we've got about 50% of these massive galaxies ending up as the cores of low redshift massive ellipticals, but it's only 50%, and that's an important point. 30% are unperturbed, 15% are consumed, and about 15% undergo a major merger, and they become well mixed by the time they get to low redshift. So here we go, Brad, if you're not too tired, we've got a quote for you here. And Khalifa data, unfortunately, I don't know how to use Khalifa data. So the last point I want to address here is that we can also account for the scatter. And this is work that we're currently putting out right now, where I showed these lines, and we can now evaluate the median number density evolution. But we shouldn't ignore the scatter, right? And this is very different scatter than scaling relations, but this is scatter all the same. If you just look at the median evolution of these galaxies, you will be able to say something about the median track taken by a galaxy, but unfortunately, there's so much scatter that's a truly incomplete picture of how these galaxies evolve. And I hope in the previous example, that point sinks home. So my suggestion is that we do 2 things. First, that we abandon the idea that observationally we can pin down what a typical Milky Way progenitor is. And second, that we move towards trying to account for the scatter and quoting that from the results when we're doing this comparison of galaxy populations across different redshifts. This is basically the last science slide. I want to show what the impact of taking into account the scatter is. Right? This is now looking at simulation data. And what we're doing is we're looking at how galaxies evolve in star formation rate and stellar mass as a function of time. And we're doing that by linking galaxy populations using one of the observational metrics. So the red line here and the blue line show either the constant co-moving number density analysis or the non-constant where we don't include the scatter. And what you see is that these end up as delta functions in their predictions for stellar mass. Right? So they end up as delta functions, which are slightly offset. Using the non-constant co-moving number density tracks, you end up recovering the median values of the actual progenitors, which are the black points in this plot. However, that's truly incomplete. You get these delta functions, you're not actually truly sampling the distribution of progenitors. If instead you take into account what the distribution of the scatter looks like, and again, fits can be provided for that, then you're able to get this great distribution here, which shows the probabilistic distribution of progenitor galaxies, given how we see the median number density evolution and scatter evolving with time. You're then able to get this prediction, which looks, of course, qualitatively different than either the constant or non-constant co-moving number density analysis. So we're encouraging people to move towards using that. Okay, so here we've got a couple more tweets. Jeff, thanks a lot for this. Sorry about your it seems that last night we were too energetic for all of us. Yeah, mine too. Last point, all the data I presented is publicly available. If you go on to the Illustrious website, you can download chunks of the data. It's very easy to navigate both the merge trees and the raw simulation output. The full data is very large, but you can get smaller chunks to just address specific topics, like, for example, the mass evolution of a specific subset of galaxies. And should you have questions, you should contact folks who have worked with this data set. We'd be glad to help. So I'll put up my conclusions and wrap up. In short, number density analysis works as a zeroth order approximation, but we can do better by using non-constant number density analysis and by taking into account the scatter. And yep, we've done this using the Illustrious data set, which is all public. I'll take questions. Thank you.
Okay, done.